Good evening, everyone. Today's talk is from Professor Arnaud Trouvé. And now he serves in the Department of Fire Protection Engineering at the University of Maryland in College Park, USA. He joined the faculty in 2001 with a PhD in 1989 and engineering degree in 1985 from École Centrale of Paris, France, and with previous experience as a combustion research engineer. Professor Trouvé's research interests include the fire modeling and the computational fluid dynamics, application of data assimilation to fire and combustion, and the physical modeling of combustion and fire-related phenomena, including compartment fires, wildfires, and explosions. Professor Trouvé is a fellow of the Combustion Institute and a recipient of the 2017 Forum Sterling Award. He has served on the editorial boards of the proceedings of the Combustion Institute programs in energy and combustion science, combustion and flame, and fire technology, and is currently on the editorial boards of Combustion Theory and Modeling and the Fire Safety Journal. Professor Trouvé is also a past chair of the U.S. Eastern States section of the Combustion Institute and a past member of the executive board of the International Association for Fire Safety Science. He is a co-chair of a recent initiative endorsed by IAFSS and called the IAFSS Working Group on Measurement and Computation of Fire Phenomena, and the current chair of a new network of leading higher education institutions and research laboratories in fire safety engineering called the International Fire Safety Consortium. And now I will give the now it's time for Professor Arnaud's Trouvé's talk.
Thank you very much, Dr. Wang, for this nice introduction. So please let me know if you don't see my screen. I'm hoping you can see it. All right, so I want to talk about simulations of wildland fire spread with OpenFOAM, and I first want to acknowledge my co-authors. So Mohamed Ahmed is a PhD student working with me at the University of Maryland, and Jason Forthofer and Mark Finney are researchers in the Missoula Fire Science Laboratory of the U.S. Forest Service, and this work is actually sponsored by the U.S. Forest Service. So wildland fires are a multi-scale problem, and different researchers are working in a different range of scales. So it's important to differentiate between the different scales present in a wildland fire problem. So here I have this little cartoon that shows that you need to differentiate between vegetation scales at millimeter size that are responsible for the production of fuel, flame scales at the meter size that are responsible for the combustion of that fuel in the gas phase, fire line scales and geographical scales that are responsible for the interaction of the fire with the local wind, the local topography, the local change in vegetation, and finally the meteorological scales at kilometer size and above that are responsible for the basically interaction with the fire with the mesoscale weather conditions. So a multi-scale problem, and here I'm going to focus on the scales that are relevant to combustion engineering, the scales of the vegetation and the scale of the flame. So computational modeling has the potential to describe physical phenomena at any of these scales, but typically because of limited computer power, any given computational solver is going to be specific to a certain range of scales. So here we differentiate between combustion solvers that resolve the dynamics at the vegetation and the flame scales, wildfire solvers that resolve the dynamics at the fire line and geographical scales at the kilometer scale, kilometer size, and finally atmospheric boundary layer solvers that resolve the dynamics at the mesoscales of the atmospheric boundary layer. And again, here I'm going to focus on OpenFOAM as a combustion solver that is going to look at the problem at scales relevant to the vegetation of the flame, roughly speaking, meter scale. In terms of an introduction, I want to review the basic steps associated with flame spread physics. So flame spread can be understood as a repeated cycle of first, heating of the unburned solid fuel. Second, the production of flammable vapors as the result of a thermal degradation that is taking place inside the solid vegetation biomass. And third, the combustion of the flammable vapors in the flaming mode in the gas phase. In this description, pyrolysis is the production of flammable vapors due to thermal degradation of solid fuel. Ignition describes either the start of pyrolysis or the start of combustion, but I will come back to that topic in a few slides, and basically these are the same. And combustion usually means homogeneous exothermic oxidation of flammable vapors in the gas phase and in the presence of a flame. But actually in the next slide, I'm going to indicate that the combustion process is more complex in wildland fires, more complex than this. So we have basically two combustion modes. There is a flaming combustion mode that corresponds to homogeneous gas phase reaction and takes the form of a usual non-premix buoyancy-driven turbulent flame. But we have also, in addition to this, a non-flaming combustion mode that is called glowing combustion or smoldering combustion. That is the combustion mode that we are familiar with because of burning fire log in the fireplace or because of burning charcoal in a barbecue. That corresponds to heterogeneous solid gas combustion where the fuel remains in solid form. And so in a fire, in a wildland fire problem, we have both flaming and smoldering combustion that are relevant to the problem. And I will come back to that. And that's one of the objectives of our simulations, to be able to describe both modes of combustion. So as I said, in the first step of flame spread is a step in which the unburned solid vegetation is heated by the surrounding flame. And this heating process takes place in the form of radiative heat transfer or convective heat transfer or the transport of firebrands. Now, firebrands is of interest to this problem, but I'm going to stay away from that problem. So firebrands designate the fact that small solid particles can break from a burning biomass. And when they break, they can be, if they are small enough, they can be transported by the fire plume and the ambient heat at distant location and start secondary fires there. So this is definitely a phenomenon that is responsible for fire spread under some circumstances and is of interest to the community, but I will stay away from that problem here and focus on the fire spread due to radiative or convective heat transfer. So if we focus on fire spread due to radiative or convective heat transfer, one of the key quantities to understand the thermal loading of solid particle surfaces by surrounding hot gases is the expression that you have here, where you have basically the heat flux to an assumed solid surface as a convective component and a radiative component. And the parameters of that heat flux are the local temperature of the gas, the convectivity transfer coefficient that depends on the local flow velocity, as well as the local shape and dimension of the solid particle that represents biomass vegetation. And the incoming radiative heat flux, called capital G here, that represents the heat loading due to radiation, is also called the irradiation. So all these external properties from the gas are relevant to understand the heat transfer to the solid particles, and I will come back to that. So in the second step of a flame spread cycle, once the solid biomass fuel has been heated, then it's going to start producing flammable vapors, and these flammable vapors are going to burn in the third step. And so this is part of an ignition sequence. So this ignition sequence has several steps here. So the first step is the heating of the solid material. The second step is the start of the pyrolysis of the production of flammable vapors. This is a phase change, and that phase change starts occurring at temperatures typically of about 300 degrees Celsius. And then finally, these flammable vapors are going to mix with ambient air and are going to start igniting through chemical reactions that takes place in the gas phase. And the details of that depends on the exact details of the configuration. So I will not go into these details here. And finally, after the ignition in the gas phase, or the flammable vapors in the gas phase, you may have transition to a sustained diffusion flame around the biomass. It turns out that many of these steps are relatively fast, and the rate limiting step is the first one, the heating of the solid material. And that explains why when we look at ignition meaning ignition of a flame, really we can call it start of pyrolysis. The rate limiting step is the heating of the solid and the start of the phase change that takes place inside the solid particle. So once you are starting pyrolyzing, the intensity of the pyrolysis process is a direct function of the intensities of what we call the thermal feedback, or the gas to particle heat transfer. So to understand what controls the rate of formation of flammable vapors, it is useful to do an analogy with evaporation of liquids. When you evaporate liquids, basically, a simple model consists in writing that the fuel mass of evaporation, the mass evaporation rate in units of kilogram per second per meter square of exposed liquid surface area, can be written as the ratio of the incoming heat flux, or the net heat flux, I should say, the net heat flux to the liquid surface divided by the heat evaporation of the liquid. So similarly, as a simple model to understand pyrolysis processes, we can write that the mass rate of evaporation of the flammable vapors produced by thermal degradation of a solid fuel is equal to the net heat flux coming from the gas phase to the solid phase, divided by the heat of pyrolysis, which is the kind of semi-empirical quantities that characterize the heat required in numbers of joule, in terms of joule per kilogram of flammable vapors produced. So this is a model that is not quantitatively accurate, so you need more elaborate pyrolysis model to describe the production of flammable vapors, but it is good enough to understand the physics that shows that the rate of evaporation, or the rate of gasification, the rate of pyrolysis, I should say, for solid fuel, is a direct function of the thermal feedback. And finally, the third step, when we have combustion, if you have combustion under the presence in the outdoors, in wildland fires, under the presence of enough oxygen, typically the combustion process is complete, and you can write that in an average sense, the heat release rate is proportional to the fuel mass loss rate times the heat of combustion. And this assumption that for outdoor wildland fires, that the combustion process is quasi-complete is good enough to predict the heat release rate. All right, so to finish this introduction, I want to show here a small, I want to show a movie borrowed from the Missoula Fire Science Laboratory, courtesy of Dr. McPhinney, that is going to show an experiment of flame spread over a surrogate fuel bed that corresponds to an array of cardboard sticks. So the flame is propagating from right to left, and the fuel for the flame spread are these vertically oriented cardboard sticks that are arranged on this inclined table here, and we have a top view of the flame, and we see the flame spreading from top to right. So I'm going to just use a couple of images from this movie. If I stop the movie, I see the typical peak and trough structure of the flame that is known to be the characteristic structure of these turbulent diffusion flames that are buoyancy driven and that spread over a fuel bed. So this peak and trough structure is a direct result of buoyant instabilities. Let me continue the movie. So if I go far enough here, let me stop here. Now you see very clearly that you have a flaming region. So this is the turbulent diffusion flame that propagates from right to left and is going to consume the unburned fuel. And then behind it, you have glowing red regions that correspond to smoldering combustion, so combustion without a flame. And finally, you have a region where the cardboard fuel is burned out and has been transformed to a small solid residue that we call ash. So you see the importance of the flaming region and the smoldering region in these problems. All right, so let me move on now to a description, after a description of the physics of the problem, a description of the numerical formulation and numerical approach to solve this problem. We use a Lagrangian Eulerian approach that borrows from previous work, in particular the development of the multi-phase modeling formulation that was developed in about now 2 decades ago by a research group in Marseille, France, in particular Bernard Portori, Dominique Morvan, and Jean-Louis Consalvi. Our modeling approach also borrows from the development of OpenFOAM as an open access code, and we are using the large eddy simulation low Mach number models available in the OpenFOAM library. Our approach also borrows from the description of pyrolysis using models that were developed by Chris Lautenberger and Carlos Fernandez-Peyo at UC Berkeley. And finally, our approach also borrows from recent developments done by the development team of FDS, the Biodynamic Simulator, developed at the National Institute of Standards and Technology in the US, and in particular, the contribution by Rudy Mel for applying FDS to 1-on-5 spread problems. So our formulation is a classical Lagrangian Eulerian approach. We solve for the gas phase processes in a Eulerian framework using large eddy simulation. And then we also solve for solid phase processes using a simplified one-dimensional Lagrangian particle models that are viewed as a submodel LES grid. Okay, so this is a classical Lagrangian Eulerian viewpoint. Let me say a few words about the pyrolysis model that is a key to this problem. So we are following the work by Lautenberger and Fernandez-Peyo. We are describing the thermal degradation process inside particles in the Lagrangian model through 4 reactions. We have a drying reaction that represents evaporation of moisture into water vapor and a solid residue that we call dry solid. Then the degradation of the solid into flammable fuel for the combustion process in the gas phase, and a solid residue that we call char. And we use 2 reactions. The first one is just driven by temperature. The second one is also driven by temperature, but requires the presence of oxygen inside the particle. And finally, a 4th reaction that describes the thermal degradation of the solid char in the presence of oxygen into combustion products and a solid residue that we call ash. In this description, the first 2 reactions are endothermic. The third reaction, that is oxidative pyrolysis, is slightly exothermic. And the 4th reaction, char oxidation, is strongly exothermic. So here I will go briefly through the equations that are solved by the Lagrangian particle model in 1D. We use a post-medium formulation. So we have, for example, conservation equation for the solid chemical species. These chemical species are the wet solid, the dry solid, the char, and the ash. And there are mass conservation equations contained on the right-hand side terms that represent the contribution of the drying reaction, the 2 pyrolysis reaction, and the char oxidation reaction. And the reaction rate, the mass reaction rate on the right-hand side are described using Arrhenius kinetics. Then we have an energy equation with a contribution of transport of heat due to diffusion, a contribution that represents transport of heat by convection due to the presence of flow inside the particle, and a contribution that represents the contribution of the different reactions. Again, 2 of them are endothermic and 2 of them are exothermic. Because we have 2 reactions that are sensitive to the presence of oxygen, we need to keep track of the presence of oxygen mass inside the particle treated as a porous medium. So we have an equation for the transport of oxygen mass, and we have a term, that equation that represents diffusion of oxygen through the particle, term that represents convection of oxygen through the particle, and 2 terms that represents the consumption of oxygen due to the oxidative pyrolysis reaction or due to the char oxidation reaction. And the flow is described using Darcy's law, where the flow rate is proportional to a pressure gradient. And finally, the formulation is completed by a pressure equation that comes from total mass conservation and the ideal gas flow to calculate the pressure profile. So the main point I want to make here is that these models are quite elaborate, and they contain a lot of input parameters. So here you have thermal properties of the different solid chemical species, the wet solid, the dry solid, the char, and the ash. You have also physical properties like the porosity or the permeability of these different chemical species. And finally, at the bottom of this table, you have the Arrhenius parameters for the kinetics of the 4 reactions that we are treating in this formulation. So a lot of input parameters, and these parameters have to be calibrated against experimental data in a careful calibration study prior to going into a 1.5 spread, and we come back to that in a few slides. The next few slides I will only have, because of lack of time, I will only go through them very quickly. These are the LES equations enhanced with terms that represent the coupling between the gas phase and solid phase processes. This is fairly classic. The only thing I want to mention is that when you look at the mass conservation equations, that represents the added mass or the lost mass to the solid particles. And these terms have a beta S parameter here that represents the volume fraction of the solid in the bed. And this is basically called the packing ratio in fire literature. The packing ratio is 1 minus the porosity of the vegetation bed. So that's an important parameter in the dynamics of wine on fire spread. We have a similar equation for conservation of momentum that looks at the effect of drag due to the presence of the solid particles. And finally, there is also an energy equation that looks at the heat that is lost to the particle to thermally heat them and degrade them. Again, for lack of time, I'm not going to talk that much about the different models. The first model that is mentioned in this slide is the classical subway-scale turbulence model, and we borrow from the literature here, so nothing special. I want to spend a minute talking about the combustion model. The combustion model here is the eddy dissipation model that comes from the 1970s and is a form of the eddy breakup model for diffusion combustion. This model uses a global combustion equation and assumes infinitely fast chemistry, and the volumetric rate of energy release is basically controlled by a turbulent timescale here that represents the mixing process between fuel and oxygen. This model is relatively crude compared to the kind of models used by our colleagues in combustion science for engine applications, and it doesn't use any information on chemistry. So I just want to make 2 comments on this. This is justified by the fact that the goal of our simulation is to predict the heat release rate. It is not to predict the detailed composition of the combustion products. So our objective is more limited, and therefore simpler models may be okay. In addition to this, and that's my second comment, we don't know in fire situations the exact composition of the fuel. Here, there is an approximate representation of the composition of the flammable vapors coming out of solid particles due to pyrolysis. This is only known with partial accuracy. And we don't know the exact details of the oxidation chemical kinetics of this particular fuel. So basically, detailed chemical models are either not available or are not fully relevant to our applications. And that explains the reason why we are going to these simple models. All right, so one quick word also on the modeling of radiation that is key in biodynamics. The variable to treat radiation in a computational model is the radiation intensity I that describes radiation energy per unit solid angle and per unit meter square. And so the values of the radiation intensity as a function of spatial coordinates and as a function also of angular direction are obtained by solving the radiative transfer equation that is presented here. And this radiative transfer equation has a contribution due to phenomena, emission and absorption occurring in the gas phase, and due to also the effects of particle and absorption of radiation energy due to the presence of particles. I don't have time to go into the details. The second line here gives the energy term units of watt per meter cubed presence in the energy equation of the gas phase due to the presence of radiation gains and radiation losses. The thing I want to mention is that these equations show two characteristic radiation length scale. Radiation length scales that is associated with the radiation effects occurring in the gas phase, and it can be written as 1 over kappa, where kappa is the Planck mean absorption coefficient, and a radiation length scale associated with radiation effects due to the presence of solid particle that can be approximated as 1 over the packing ratio times sigma, which is the surface to volume ratio of the solid particle. And so this is essentially the diameter of the solid particles divided by the packing ratio. These radiation length scales allow us to differentiate the optically thin and optically thick regimes. When these radiation length scales are large, that means optical regime is optically thin. And when these radiation length scales are small, that means that our radiation problem is optically thick. Now, kappa, the Planck mean absorption coefficient, is a function of CO2 and H2O concentration, and also a function of soot volume fraction. That's actually a problem because that means accurate modeling of radiation requires accurate modeling of soot, which is a difficult task, especially given that we have combustion models that have no information on chemistry. So a usual bypass simplification used in finding constraints in assuming that gas phase absorption can be neglected and that gas phase emission can be written as proportional to the combustion volumetric heat release rate. And using a coefficient of proportionality here, chi-rad, that is an empirical factor that we call the fraction. So this simplification we use here, we're going to use a prescribed global radian function to describe radion emission from the flame. All right, so back to the coupling between gas phase and solid phase processes. The mass coming out from, especially the fuel mass coming out from the particles, and that are going to provide fuel required by the flaming combustion process, and have the heat that goes from the gas phase to the solid phase to basically sustain flux. Again, depends on the local gas temperature and the irradiation, or the also known as the incoming radiation heat flux. The incoming radiation heat flux is obtained as an integral of the radiation intensity over the 4 pi solid angle, and basically comes out from the calculation allowed by the radiative transfer equation. So the radiative and transfer equation gives I, and then we can calculate G as an integral of I. So here I want to focus on the problem of determining H, the convectivity transfer coefficient. So this is actually an important problem that is still unsolved. The convectivity transfer coefficient plays a dominant role in the spread of these flames. Unfortunately, we don't have a lot of information on this convectivity transfer coefficient. So typically, in a model, we use engineering correlations coming from different applications. So here you have an example of the calculation of the convectivity transfer coefficient using a Nusselt number correlation, when a Nusselt number is described as a function of the particle Reynolds number. Here we assume a cylindrical shape particle characterized by a diameter d. And so basically H is a function of the local flow velocity and the diameter d of the particle. You can make these correlations a bit more sophisticated and introduce the effect of blowing. Blowing accounts for the decreased values of H associated with the transpiration of mass across the particle surface. But I want to more focus here on what these correlations are telling us about the effect of changing D. So on the right-hand side here, I'm plotting H as a function of the diameter D. And you see that for large particle diameters, the value of H is on the order of 10 to 20 watt per meter square per Kelvin, which are typical values used, for example, in compartment fire simulations. But for smaller diameters, for diameters on the order of 1 millimeter size, then the value of H can reach values above 100 watt per meter square per Kelvin, or are basically an order of magnitude higher. So that means that small particles are going to be basically very sensitive to convective heating or convective cooling, whereas large particles are going to be much less sensitive to this. And that means that the behavior of small particles and large particles is going to be quite different in wildland fire scenarios. So in addition to H that characterize transfer of heat, we have to look at the convective mass transfer coefficient, H mass, that characterize the transport of oxygen mass to the particle, the oxidative pyrolysis reaction and the Char oxidation reactions, very sensitive to require the presence of oxygen and very sensitive to the mass flux of oxygen that goes from the gas phase to the core of the solid particles, and described by H, and using by this parameter H, and this convective mass transfer coefficient is directly related to the heat transfer coefficient using standard engineering practice. There is also the need for a description of the drag coefficient, but that's more classical, and here it is less important, so I will not mention more. All right, so that describes all the models that have to be put together to get to a simulation of flame spread in a wildland fire scenario. So again, here we're going to look at a simplified configuration, a surrogate fuel bed that corresponds to a vertically oriented cylindrical shape sticks of pine wood. And this vegetation fuel bed basically is going to be characterized by the height of the vertical pine wood sticks, their diameter, as well as the packing ratio that describes how many of these wood sticks we have per unit meter square of ground surface. So before we go to result of simulation, I want to indicate again that we need to carefully calibrate the pyrolysis model we're using. So this is a model that is available for pine wood. And here we are showing basically calibration experiments against calibration simulation against experimental data coming from macroscale experiments known as thermogravimetric analysis experiments, TGA experiments. Here you're looking at the variation of the mass loss rate as a function of controlled temperature in the experiments for these thermally thin particles of pine wood. And you are seeing comparison between lines that are the models and symbols that are the experiments for different atmosphere. So on the left, you have the experiment conducted in pure nitrogen, and on the right, you have the experiment, the same kind of experiments performed in a mixture of nitrogen and oxygen, and you can look at the effect of the presence of oxygen on thermal degradation. This calibration also involves comparison with experimental data done at the bench scale. Here, cone calorimeter experiments that corresponds to thermally thick now samples of pine woods that are exposed to fixed values of radiation heat flux. So this is the value of G of the irradiation, the incoming heat flux on the solid pine wood sample surface. And here you see comparison again between experiment and experimental data, between simulation result and experimental data for different atmospheres, pure nitrogen, pure air, or mixture of nitrogen and oxygen. The parameters, again, in our simulation of our vegetation fuel base are the particle mass density, the particle surface to volume ratio, or in other words, the diameter of the solid particles that are present in the fuel bed, the fuel moisture content, the heat of combustion of the flammable vapors produced by the pyrolysis process, the height of the pine wood sticks, the packing ratio that describes the number of pine wood sticks per unit ground surface area. And finally, the environmental conditions, the wind velocity. We are considering flat terrain here, so the angle of the slope is just 0. Some important derived quantities are the bulk mass density of the fuel bed, which is basically the product of the packing ratio times the particle mass density, the mass density of pine wood. The solid mass load that characterizes the mass of solid present per unit meter square of the ground surface, and that is expressed as the bulk mass density of the vegetation bed times the height of the vegetation bed. And finally, an important parameter for combustion, which is the effective fuel mass load in units of kilogram of fuel consumed per unit meter square of ground surface. That is related to the solid mass load times 2 factors. So you have a factor here that accounts for the fact that not all the mass of the solid is turned into fuel for the gas phase flaming combustion process. And so you have the yields associated with water evaporation or with pyrolysis. And there's a second factor that is contains more physics here, and that is the consumption, the fuel consumption efficiency factor, or the particle consumption efficiency factor, that represents the fact that not all the solid fuel mass will be actually completely thermally degraded. So the thermal degradation process may not be complete, and this factor accounts for this. And so, and I will go back to that and see that in the simulation. Here, before I present the simulations, some representative simulation results, I want to say that the 2 main global parameters for flame spread are the heat release rate of the flame and the rate of spread of the flame here in the direction of the wind. Using standard mass conservation arguments, you can show that the heat release rate of the flame and the rate of spread of the flame are related. This is the BRAM expression here. So in this expression, I'm assuming a quasi two-dimensional, statistically two-dimensional behavior. So the flame is assumed to spread as a linear line fire. And in that case, the heat release rate is replaced by a quantity known as the fire intensity, which is heat release rate per unit length of the fire line. And you can show that using BRAM expression, that the fire intensity can be expressed as the effective fuel mass load times the rate of spread times the heat of combustion. So this shows that heat release rate and rate of spread are about the same thing, but they're not quite the same thing because the effective fuel mass load here has a parameter built into it that was presented in the previous slide, which is the particle consumption efficiency factor that accounts for the fact that not all the particle mass will be consumed by the passing flame. And therefore, there is some information here that shows that basically fire line intensity and rate of spread are related, but are not exactly the same quantity. So let me move on now to the numerical configuration. So we have a domain that is 152 meters long, 40 meters deep, and 40 meters high. This is flat terrain. We assume in this representative simulation wind velocity at 2 meter elevation of 5 meters per second. We have a boundary layer profile, and we also introduce in the inlet of our domain turbulent fluctuations. We are considering cylindrical shape vertical sticks of 2 millimeter diameter in the baseline configuration. These sticks are 0.4 meter high in the vertical direction. The packing ratio is 0.5%, and we use a prescribed global radiant fraction approach. A quick word about our choice of grid resolution, which is going to be 10 centimeter. We compare that resolution here to the characteristic length scale of the problem. So we have the elevation of the fuel bed, 0.4 meter. We have the radiation penetration length scale, which is also 0.4 meter here. And we have the flame scales, the flame length, the flame height, and the flame depth explained in this diagram here. And we will see when we look at the simulation result that these length scales are meter scale and typically above 1 meter. That explains that our choice of grid resolution of 10 centimeter, 5 centimeter would be better, but we, in our baseline simulation choice, we typically settle for 10 centimeter, which is marginal to resolve the radiation penetration length and the vegetation height, but is good enough to describe the flame geometry. We've done a grid conversion studies that shows that there is not a lot of difference between 5 or 10 centimeter simulation. I want also to say a word about now the grid resolution required in the Lagrangian particle model. So here is a result of the Lagrangian particle model used here as a standalone model. This model corresponds to a 10 millimeter diameter cylindrical particle heated during 1 minute at a level of 60 kilowatt per meter square incoming radiation heat flux. And the local velocity is 1 meter per second. We see here the mass loss rate as a function of time, and we see two phases. The first phase that corresponds to basically pyrolysis, and that phase is sustained by the external heat coming into the particle. And the second phase that corresponds to smoldering combustion that is self-sustained and it continues even when the external heating is stopping. So you see in this particle simulation, this particle response simulation, a nice transition from basically flaming combustion to smoldering combustion here. If I look at two different snapshots at the details of the temperature profile on the left or the volume fraction of char and ash profiles on the right across the particle surface here, 5 millimeter, is on the right, and the particle core is on the left in these diagrams. You see the high temperatures achieved inside the solid particles, typically temperatures above 1000 K. And you also see on the right the displacement of the char oxidation reaction from the core region to from the surface region of the particle to the core region of the particle. So the char oxidation region is a region where char is transformed into ash. Here on the left, we show the distribution of oxygen inside the porous particle. So oxygen is coming from the gas phase and is diffusing into the particle. And you can see here that actually the char oxidation reaction is oxygen diffusion limited. There is no oxygen mass in the core of the particle. All the oxygen that diffuses into the particle is consumed by the char oxidation reaction. And on the right, you see the volumetric mass reaction rate of the char oxidation reaction. And I want to use this to say that the thickness of these reaction regions are quite thin, on the order of 0.1 millimeter. And that explains why in our simulations, we need a very fine grid inside the Lagrangian particle model. We use 25 micron resolution. Okay, now it's about time, so bear with me. I need about 10 minutes to finish. It's time to show some representative results. So using a 10 centimeter resolution in the gas phase solver, we have about 7.4 million grid cells, 2.4 million particles. Again, our typical CPU cost here for 1 minute of simulation is about 25,000 hours. And we typically simulate this flame spread for 4 minutes. So roughly speaking, we have about 100,000 CPU hours in one simulation of these flame spread problems. So some preliminary results. So here we see that we have first estimated rate of spread values coming from the well-established raw thermal model used in wildland fire literature. According to the raw thermal model, the rate of spread for our conditions should be on the order of 0.33 meters per second. We simulate 0.37 meters per second, which we think is adequate. Empirical correlations for the fire line intensity predict a heat release rate of 3 megawatt per meter of length of fire line, and we simulate 3.3 megawatt per meter, which is again within 10% of the empirical value, which we think is adequate. A quick comment is that this heat release rate here, this fire line intensity, characterizes a flaming combustion. If we add the contribution of smoldering combustion, we end up with an additional 1.84 megawatt per meter. So the total heat release is actually 5.1 megawatt per meter. And basically, the heat release that takes place inside the particles in a non-flaming mode account for about 36% of that total heat release. If we look at the flame scales, we find that in our simulation, the flame height is on the order of 5.5 or 5.6 meter. The flame depth is on the order of 1.5 meter. And behind the flame, we have a smoldering region that is about 8 meters long. So the total depth of the zone where you have mass loss activity is close to 10 meters in this simulation. And that justified the fact that 10 centimeter grid resolution is adequate to resolve these dynamics. So let me show some animations here of the simulation. So here we're looking at temperature isocontours in the gas phase and in the solid phase to identify the flame and also the hot region where the particles are basically thermally degrading due to pyrolysis and smoldering. These visualizations show the classical peak and trough structure of the flame that is a result of buoyant instabilities and that has been observed experimentally. Here, I want to go in a little bit more details and show a modified configuration where we have a small patch in the X domain of particles that are going to contain not only the 2 millimeter particles that we have in our baseline configuration, but also in addition to this, larger particles. So we have mixtures of 2 and 10 millimeter particles or 2 and 20 millimeters particles in our simulations. And this is done basically to show the sustained smoldering process even after the flame has gone through. So here, again, the flame is propagating at this point across a bed of 2 millimeter pine wood particles. And then it's going to reach larger particles that have a 10 millimeter diameter. And the flame is going to spread further, keep spreading. And the larger particles are going to take a long time to complete the thermal degradation process through smoldering. So these simulations are a nice way to show the successful transition from flaming combustion to smoldering combustion in the case of these 10 millimeter particles. So if we want to characterize the environmental conditions experienced by individual particles during the flame spread process, we see that in the vicinity of the flame bed, the temperature of the gas reaches temperature on the order of 1200 K peak value. The velocity of the gas, which is peak values between 2 and 3 meters per second, it is a little bit lower than 5 meters per second wind velocity specified at 2 meter elevation because of the lower elevation of the fuel bed and also because of drag effects inside the fuel bed. And we have also access to good oxygen, except when the flame is passing through, and we have reduced level of oxygen when the flame is present in the vicinity of these particles. If I look at the response of the particles, the first thing you want to study is the net heat flux. So we have here on the left the total net heat flux, and then the next two slides correspond to the convective contribution and radiative contribution to the net heat flux. We see that these heat fluxes start from positive values that correspond to the heating process due to convective and radiative heat transfer, to finally negative values that corresponds to a cooling phase. Once the particle has reached a very large temperature above 1000 K, then basically the particle will be cooled by convection and radiation when it is exposed to a cooler environment after the flame has passed. So the main point I want to make here is that the net heat flux is an attractive quantity that contains a lot of physics, but it's actually difficult to interpret because it has changing values from positive to negative and strongly time-dependent values. And also, you realize that the net heat flux contains information on the heat loading through the temperature of the gas or the incoming radiative heat flux, but also contains information on the response of the particle through the presence of the temperature of the exposed surface. So we are trying currently to differentiate and identify the contribution of the external heating without the contribution of the particle response. And we've introduced a new variable that we call the pseudo-incident heat flux that looks at the part in the net heat flux that represents external quantities and that doesn't depend on the particle surface. When we do this, then we can clearly identify the values of external heating and the duration of external heating on the order of 30 seconds to 40 seconds here. And that allows us to basically nicely identify when the particles are externally heated by the passage of the flame. This actually quantity can also be used to differentiate between the contribution of convection and the contribution of radiation. And we find that for small particles, the contribution of convection and radiation is about the same. So we have a mixed mode of heat transfer to the particle. Whereas for larger particles, the contribution of convection is very small and we are dominated by radiation. And this is explained by the lower values of H that we find for larger particles, which means that the impact of convective heating is much reduced when you go to larger particles. So bear with me, I'm now have my last couple of slides before conclusion. So if we look at now the issue of fuel consumption, of the completeness of the particle thermodegradation process, we compare here the thermodegradation of small particles and larger particles. We see that small particles undergo complete thermodegradation. And we have basically transition, we have transformation of wet solid into dry solid, and then dry solid into char, and char into ash. Okay. And this process is complete. Whereas for larger particles, we have a complete transformation from wet solid into dry solid, but only partial transformation of dry solid into char. And so after the flame has passed, we still have some unconsumed char that is left behind. So we have partial fuel consumption, partial production of fuel for these larger particles. And we basically have compared different sizes of particles, and we find that basically we have two types of particle behavior, complete fuel consumption for small particles with both flaming and sustained smoldering, and only partial fuel consumption for larger particles with no or limited smoldering. Okay, and that's an important aspect of fire dynamics. So my conclusion slide here, we've developed an OpenFOAM-based computational capability for detailed simulation of wildland fire behavior at vegetation and flame scales. We solve for the thermal degradation process inside the solid vegetation at millimeter scale or even sub-millimeter scale. And we also solve for the gas phase processes at centimeter scale. We describe the exchanges of mass, momentum of heat associated with thermal degradation of the biomass, combustion, radiative and convective transfer, and the turbulent flow. And we, again, do all of this at vegetation and flame scales. The simulations successfully simulate the transition from flaming to smoldering, as well as the transition from complete consumption to partial consumption of the particle and partial production of fuel. We believe that this kind of computational capability can unravel the details of the physics associated with coupled phenomena between gas phase and solid phase processes at these meter scale relevant to vegetation and flame processes, and that are in part controlling the wildland fire behavior. So with this, thank you very much. And I will stop here, and I'm open to answer any question that you might have.
Thanks for your wonderful talk, Professor Trouvé. So I found one question from the audience. Let me read it for you. Like all computational models, Firewinds is based on certain assumptions and simplifications that may not always reflect the real world. This can limit its accuracy in certain scenarios or for certain types of files.
So I think when you are using a computational model, you have to differentiate between the numerical quality of the model and the physical modeling, and the numerical, so the physical accuracy of the computational model that represents the physics. So in Firewinds is a low Mach number solver that has numerical techniques that are second order accurate, and we've done numerical tests, and that does the job of accurately simulating the gas phase physics with limited numerical errors. So we are satisfied with this aspect of the question, I think. The low Mach number formulation is fully adequate here. Our Mach numbers are much below 0.3, so we can stay away from compressible flow physics. Now the physical modeling accuracy is the main issue, and that's part of the job that we are, that we are doing when we run these simulations. We are trying to improve the accuracy of these physical models. So here we have a range of models that have some limited domain of validity, each one of them, but we are focusing on, we are basically accepting the limited accuracy of each one of these models in the gas phase or the solid phase processes, and trying to focus on unraveling the physics in the coupled phenomena. So with this, a lot of the answers that we are bringing, or a lot of the insights that we are bringing are tend to be more qualitative than quantitative because of the limited accuracy of the physical models we are using. But in the end, the final way of making sure that we are quantitatively predictive is through a comparison with experiments. So we have this range, this suite of validation exercises at the macro scale and the bench scale for the pyrolysis model. And then when we go to wildland fire behavior, we are comparing to experimental data available in terms of rate of spread. I want to make just one last comment on this. The number of the details of experimental data is fairly limited for wildland fire. So typically what you get in an experiment like a prescribed burn, where you have a wine on fire that propagates through a flame bed, or even a laboratory scale experiments like the one in Missoula Fire Science Laboratory, what you get out of these experiments is often a single value, which is the rate of spread. Okay, that's not a lot of information. Of course, my colleagues in Missoula have added diagnostics that we are comparing to, and we are doing these with now simulation of cardboard sticks that are similar to the one that they use in the experiments. But I think, again, going back to my need of validation, my comment on the need of validation data, this is rapidly changing now because people who are doing wild on fire studies in the field are adding new diagnostics with even visualization of fire line as a function of time, with great spatial and temporal accuracy using drones to visualize the displacement of the fire line in real time. And all these data are going to give us much more information for validation. So right now, I want to circle back to the old question. I recognize with humility the limited quantitative accuracy of the simulations we're doing, but I think this is going to improve quite rapidly with the availability, the wider availability of quality validation data that I see coming very soon now.
Okay, here is another question from the same person, Praditadas. Can Firewinds be used to model the spread of fire through combustible materials, such as furniture, carpeting, or insulation? If so, how does it handle the interaction between the fire and these materials?
Yeah, can you repeat the question? I didn't understand everything in the question.
Oh, sorry. Can Firewinds be used to model the spread of fire through combustible materials, such as furniture, carpeting, or insulation? If so, how does it handle the interaction between the fire and these materials?
Yeah, thank you for this question. This is a good question. So we are looking at, the answer is yes, it can. I mean, we have basically a smoldering combustion inside the vegetation biomass that we simulate in some way. So when you have basically a combustion that propagates inside a polyurethane foam, for example, what you have is a smoldering wave that propagates inside that foam. If you look at, also timber material, you have the same problem. You have flaming outside of these materials, and inside of these materials, you have a smoldering wave that propagates from the exposed surface to the core of the material. And that's very similar to what we are doing. So the same kind of models that we are looking at, that we are developing and that we are using here for wine on fire applications can be used to simulate the burning process of these materials. Yes.
The third question is from Ahmed Baha. Thanks, Professor Trouvé, for this nice presentation. What difference would you expect in terms of results if you use the more detailed kinetic mechanism in your combustion model? May it be worth to try using detailed mechanism for pyrolysis combustion in such multi-scale simulation?
Yes, thank you for this question. This echoes some comments I tried to make when I talk about the very crude combustion models we're using typically for fire simulations. So the question of whether you need more is valid. So first, there are applications where you need more. There is increased interest in calculating, the composition of the fire smoke for wine on fire application. So if you want more information on the detailed chemical composition of the smoke, certainly you need to bring detailed chemistry information. That's also valid for compartment fire simulation. What kills people in fire is the presence of toxic species like carbon monoxide or hydrogen cyanide. So you would like to be able to calculate and predict the presence of these species. So today we cannot. So, but going back to the problem of heat release rate, even there is one problem where we may need detailed chemistry. It's the problem of predicting the soot. Okay, soot is important. So I think I'm happy with not having a lot of detailed chemical information to predict the heat release rate of the fire. I'm okay with that, and I think the kind of models we've had are robust and at the correct level of accuracy at this point for heat release, again, predictions. But we need to calculate the soot because the soot is a dominant factor in radiation heat transfer. So right now we bypass that problem by user prescribing an empirical value of the global radiant fraction. But that approach doesn't work for every application and is a placeholder rather than a satisfactory modeling solution. And so to go beyond this, we need soot modeling. And to do soot modeling, we're going to need more information on chemistry, maybe chemistry of the flame and chemistry of the soot formation and oxidation. So that requires better models there, yes.
Okay, thank you for your answer. Okay, the fourth question, okay, from Pradipta again. Can FireFOAM be used to model the impact of fire on human occupants, such as the potential for smoke inhalation, heat exposure, or structural collapse? If so, how accurate are these simulations?
So thank you for that question. There are two questions. One is structural collapse, and the other one is impact on human behavior. And so let me start with the first one. Human behavior is related to my answer to the previous question. To be able to know the impact on people, you will need to be able to calculate the CO or the HCN content of the smoke. To be able to, these are the species that incapacitate people and kill people in fires. And so this, again, is not something we know how to do today, but that's something that is needed for the future. And that requires more detailed chemical information in our combustion model. The second part of the question, which is structural collapse, that requires understanding heat transfer between the gas phase and the solid structure in a compartment 5 scenario. And that is done today. And this is something that we can do relatively easily. So we calculate the amount of heat that goes from the gas to the solid phase, very much like we calculate this in the present simulations today, going from the gas phase to the solid vegetation, biomass vegetation. And then we can predict the response of the structure as it gets heated using a structural engineering model.
Okay, maybe I will give the speech to Huangwei. Huangwei, do you want to say something?
Okay, Professor Trouvé, thank you very much for your nice presentation. Okay, I know you will have other commitment after the webinar, so we will not, keep you long here. Okay, so if there is any question from the audience, maybe can write to Professor Trouvé for further discussion. Okay, and we will also upload the video into YouTube channel. So can also, watch the webinar there. Okay, thank you very much. Yeah, thank you very much, Professor Trouvé, for a very nice presentation.
Thank you very much for the invitation.
Yeah, okay. Yeah, thank you. Have a great day.
Bye, everyone.
Bye-bye.
Have a good day. Yeah, bye-bye. See you.
Bye.